Hey guys, Mr. T here. This is another video. This one is on multiple optimal solutions when you're doing linear programming. Multiple optimal solutions when you're doing linear programming. So in some cases there can be more than one optimal value for the objective function when you do the vertex objective function table and you complete it to find the optimal solution, which you would have seen in the previous two videos. This would occur when the slope of the objective function equals the slope of any of the simplex boundaries. So that means that the vertices and any valid points along the boundary between those two vertices are also going to be optimal solutions to the problem. Not just one point at a vertex, because we've previously seen that when you're finding the optimal value of a linear objective function, it occurs at a vertex. If you actually find that you've got two of the same optimal value from two different vertices, well, any point along the boundary between those two vertices is also an optimal solution. So all the points you need to check and propose them as solutions. So you're going to have multiple optimal solutions. So to see how this works, we need to run through an example. This example is going to be largely pre-done because obviously you've seen the previous videos had to be cut down very much to get them to fit. So to fit this into one video, I want to start from like sort of halfway through the process. So a store can sell every gift basket it's able to make. Small basket contained 5 chocolates, 1 balloon, 12 roses. Large baskets, 10 chocolates, 6 balloons, 12 roses. Store has a stock of 80 chocolates, 36 balloons, 168 roses. So you can see these are the limits already. These are what are going to define the constraints. Small baskets sell for $20, large baskets for $40. What combo of small and large baskets should they make to maximize their income? So we're trying to find an optimal value, which is going to be a maximum, and that maximum is going to be for the linear function of revenue, or this total selling price of these baskets. So in the previous video, the little extra one for linear optimization, we had the little steps that I defined for you. So step 1 was define the constraints and draw them very accurately. So often it's good to tabulate. So I'll let x be the number of small baskets because the question is asking me how many baskets. So we'll let those define what our variables are going to be. X is number small, y is number large, and I've tabulated this information. And you can see how I've underlined the different numbers in the question that are going to set out our constraints. So 5 chocolates, 10 chocolates in the large, 5, 10, and the number defining the number of chocolates overall is going to be 80. 1 balloon in the small, 6 balloons in the large, 36 balloons in stock, 12 roses, 168 in stock, and the selling prices of the different baskets are here. When you total them up, I've already told you before, it helps to total them up so you can see what the constraint's going to be. And so your chocolates constraint is going to be 5 times by the number of baskets plus 10 times by the number of large baskets. Has to be less than or equal to 80 because that's all they've got to play with. Balloons is going to be 1 balloon plus 6 balloons in the large basket is going to be less than or equal to 36, and 12 roses in the small, 12 roses in the large, less than or equal to 168. And I've already gone and found the intercepts here by substituting 0 into x and y to find those intercepts for general form. I've also done the second part of step 1, which is to tabulate and draw accurately. I've done as accurately as I can on this slidey screen with the slidey rulers. So here we go, I've done the constraints. So step 2 is shade the feasible region to shade feasible region, or the simplex. I'll do that in red. No, actually I'll do it in green. It's less than or equal to all of these lines, so it's going to be underneath. It's going to be down here. Now 3. Identify all feasible solutions. 3. Identify all feasible solutions. Now, we have said in previous videos that when you're optimizing a linear objective function, the optimal value is going to happen at a vertex. So we don't need to do all of these different points inside. The optimal value is only going to occur at a vertex, so we only need to find the coordinates of each of the vertices of this simplex and test those for optimal values. So this one is 0, 6, this vertex is 6, 5, this vertex is 12, 2, this vertex down here is 14, 0, and this one is 0, 0. So I've identified all the feasible solutions. I haven't wasted time finding all of these. Yes, they're feasible solutions, but they're definitely not going to be an optimal value because they're not at a vertex. And one of the lucky things we have for linear programming in the simplex algorithm is that the optimal value is always going to occur at a corner, not inside. Define the objective function, number 4. Well, we're trying to maximize the revenue or the selling, so this is the objective function here. Step 4 was to define the objective function is going to be 20 times by the number of small baskets plus 40 times by the number of large baskets because that's how much they sell for. Create a feasible solution objective function table, so we can do that in here. Also known as a vertex objective function table, so feasible solution vertex on the left hand side, objective function on the right hand side, which was 20x plus 40y. That's my table done. Now I have to put in those vertices 0, 0, 0, 6, 6, 5, 12, 2, one more, 14, 0. And now we find the results of the objective function on the right hand side. 0 times by 20 is 0, plus 0 times by 40 is 0 is equal to 0. 0 times by 20 is 0, plus 40 times by 6 is 240 equals 240. 6 times by 20 is 120, plus 5 times by 40. 5 times by 40 is 200. 320. 12 times by 20 is 240, plus 2 times by 40 is 80. That's also 320, and 14 times by 20, what is that? 280, 0 times by 40 is 0, 280. So here you can see two optimal values for the objective function, which is step 6, finding the optimal values. Find optimal values. They were 320. So this is what the new part for this video is about, is when you have found two vertices that have the same optimal value, that means every valid point between those two vertices, so we've identified that 6, 5 and 12, 2 are producing optimal values, those two. Every valid point between those as well is going to result in an optimal value too. We can't have half baskets, so it has to be whole number values. So we've got another one here which is 8, 4 along this line. And we're going to have another value here, 10, 3 along this line. Because we have shown that the objective function is going to be maximum here and here. So the objective function is going to be a line that's like going along exactly between these two lines. So anything along this line here between those two vertices that is a valid solution is also going to be an optimal solution. There's going to be multiple optimal solutions here. All of these are optimal solutions because they're whole number and they're going to meet the criteria. So we can double check that. 8, 4 and 10, 3. 8 times by 20, 160, plus 4 times by 40, 160. That's going to be 320 as well, so equivalent. And 10 lots of 20, 200, plus 3 lots of 40, 120. That's also going to be 320. So you can see these valid points also are going to give the optimal value, plus 2 more optimal values. So we've done step 6, find the optimal value. Step 7, we need to answer the question in sentence form. What were we asked to do in the first place? How do we maximize income? Therefore, to maximize income, the store can sell the following combos of large and small baskets. Small and large. Put them in a nice little table here. 6, 5, 8 and 4, 10 and 3, and 12 and 2. Alright, and to just triple show you what all of this calculation is showing, if we drew the objective function, so I might draw it in purple. We've shown the objective function, the optimal value is 320, so 20x plus 40y is 320. X-intercept of that is going to be 320 divided by 2, 16. Y-intercept is going to be 320 divided by 4, 8. So if we drew a line for the objective function, it's going to be y-intercept 8, 16. So the objective function for the optimal value of 320, because that's the most they could sell their combination of baskets for, is this purple line here, which you can see meets the simplex along that particular boundary. So those 4 valid points there, the 2 vertices, and the 2 valid points between them are all optimal solutions. So that is just showing you what is meant by one of these linear optimization problems, having multiple solutions. Hopefully that helps you out, and I'll see you in the next video.